So a great last problem to wrap up our chapter on 3 different types of reactions. Sample problem 4.14 asks us to identify the type of redox reaction that we have here, as well as kind of putting all of this together, writing balanced molecular equations, total and net ionic equations for the question in part C, identify oxidizing and reducing agents for everybody. Okay, so just something to kind of point out here, I didn't specifically mention it yet, but there's 4 types of redox reactions that we can see. We can see a combination reactions, and that's where we're going to have 2 or more reactants. One of them generally is an element forming a new compound. A decomposition reaction, we're going to have 1 compound basically forming 2 or more products, one of them tending to be in its elemental form. Single displacement reactions, we're going to see pure elements on each side where we're kind of swapping who gets to be a pure element and who gets to be an ion. Combustion reactions, again, we've seen combustion reactions pretty much in every chapter so far. It's the process of combining something with oxygen. Oxygen again being a pure element and then ending up in water and carbon dioxide clearly indicates that that's a redox reaction. Okay, so we've got 3 examples here, 3 reactions. Again, chapter 2, we need to kind of put these all together into a balanced chemical equation, identify or assign oxidation numbers so we can see who's being oxidized and reduced, kind of putting it all together here. All right, so let's work on problem A here. Solid magnesium and gaseous nitrogen react to form magnesium nitride. So putting this together before we worry about balancing it, we've got solid magnesium reacting with nitrogen gas, which is going to be diatomic. Magnesium nitride. Magnesium is going to be +2. Nitride is 3-. So that's going to be Mg3N2 once we go through our crossover approach. Balancing this, we're going to put a 3 in front of the magnesium, and we have our 2 nitrogens already from our diatomic gas. Okay, so that is our balanced molecular equation. We need to assign oxidation numbers so we can identify who's being oxidized and who's being reduced. So magnesium in its elemental form and nitrogen in its elemental form have oxidation numbers of 0. When we have an ionic compound that has monatomic ions, the oxidation numbers are simply the charges on those ions. So it's going to be +2 for magnesium and -3 for nitrogen. So magnesium here, going from its elemental state with an oxidation number of 0 to magnesium as a divalent cation, means we've increased the oxidation number. That means that species has been oxidized, which means it is the reducing agent. Nitrogen, going from its elemental form, N2, oxidation number of 0, to nitride, which has a -3 charge, means we've decreased the oxidation number, which means this species has been reduced, and it is the oxidizing agent. Pretty straightforward for that problem. This next problem is really important to show for a couple of reasons. The first is it's the first time we've seen a peroxide. And remember, peroxides are unique because this is the case where oxygen will have an oxidation number of -1. Okay, so we're going to have H2O2. That's what hydrogen peroxide is. This is a we forgot we were supposed to kind of label what these were. This first one is a combination reaction, right? As the name implies, we're combining 2 things together. One of them is a pure element, and we're making a new compound. The reason I was reminded to say that is I was going to say, in this reaction, hydrogen peroxide decomposes. So this is a decomposition reaction. It decomposes to water and oxygen gas. Balancing this chemical equation means we need to put a 2 in front of our H2O and then a 2 in front of our peroxide. So again, this is a decomposition reaction. Going through and assigning oxidation numbers. Hydrogen is always going to be +1. In a peroxide, oxygen is -1. And we can see this works out here. -1 taken 2 at a time means we've got -2. Hydrogen at +1 taken 2 at a time means we've got +2, which means we've got a charge of 0 for that neutral compound. So that's consistent with kind of the formalism that we had for assigning oxidation numbers. It's consistent with that oxygen being -1. So even if you didn't remember it, if you work from hydrogen, you would have gotten a -1 for that oxidation number. Over here with water, we've got -2 and then +1 for those oxidation numbers. And then oxygen over here is in its elemental form. So a couple of things are unique with this problem that you want to take note of. The first, in dealing with a peroxide, we see a unique oxidation number for oxygen, -1. The other thing that's unique is we see oxygen going to two different oxidation numbers. One case where it decreases its oxidation number, and one where it increases its oxidation number. So again, we're going to write both of these down. Oxygen is -1 on the reactant side. In one case, it goes to oxygen 2- when it goes to water. That decrease in the oxidation number indicates that it's reduced in that part of the problem. But another atom in peroxide goes from oxygen -1 to oxygen 0. That increase in oxidation number indicates that that oxygen atom has been oxidized. And again, if we're identifying these, this would be the oxidizing agent, and this would be the reducing agent. Okay, so that's not a problem to have one oxygen atom here going and being reduced and the other one going and being oxidized. All right, last problem here in our chapter 4. We've got elemental solid aluminum reacting with lead nitrate, lead 2 nitrate, so it's PbNO3 aqueous. We generate aluminum nitrate and solid elemental lead. So hopefully what everybody can see here is this is one of these single displacement reactions. Okay, and in our single displacement reaction, we have pure elements on each side, just kind of reviewing here. Single displacement, we have pure elements on each side, and we're kind of swapping who gets to be the pure element and who gets to be the ion. So hopefully it's pretty straightforward here. Aluminum goes from aluminum 0 to +3. Lead goes from +2 to elemental, so oxidation number of 0. And you actually could go through and assign oxidation numbers for these nitrates, but they don't change. Nitrate really is a spectator in this redox process. So nitrate here, I almost heard 2- there. Nitrate is a spectator in this redox process. Okay, so thinking of it in that case, this problem asked us to write the net ionic equation for part C. So what we really can say is we've got aluminum in its elemental state, solid, reacting with lead 2+ ions in an aqueous sense, and generating aluminum 3+ ions, aqueous, plus lead in its elemental state. Okay, nitrate being a spectator is not going to appear in the net ionic reaction. We can see that aluminum here, we increase the oxidation number, which means that it's oxidized, which means, again, it is the reducing agent. We can see that lead goes and decreases its oxidation number. So it is reduced, which means it is the oxidizing agent. So last problem here to kind of sum up oxidation numbers, identifying if redox chemistry is happening, specifically identifying if it's a certain kind of redox chemistry. And again, when we have redox chemistry, like we have in part C, that has spectator ions, we can write net ionic equations.